Now I am going to discuss about the oxidation of fat first, right? Oxidation, that is fat oxidation. Oxidation of fat, right? So far we discussed about basic principles of the fats. Fat consists of glycerol and fatty acid. Certain important facts regarding the fatty acids, omega-3, omega-6 type fatty acids, integrated, unsaturated, everything we discussed, right? Then today I am going to start the fat oxidation. Oxidation means actually fat more likely to interact with the oxygen. Fat more likely to interact with oxygen. So that is actually oxidation of fat. So due to oxidation, as a byproduct, most of the fat contained food, right, produce different types of products. Right? Some are aldehydes, some are alcohols, some are ketones, some are ethers, right? Aldehydes, ketones, ethers, like different types of compounds produced as byproducts of the oxidation. Right? And other way, due to this low molecular weight compound formation, food odor become very bad. Right? Objectionable odor you can feel due to oxidation of fat due to this fat. Right? Then if we think about the oxidation process of the fat, so we can divide oxidation process into three types of oxidation. Right? One is photooxidation. Photooxidation. Second one is photooxidation. Third one is enzymatic oxidation. Right. So there are three types of oxidations we can discuss regarding the fat: photooxidation, and enzymatic oxidation. So in photooxidation, there is the involvement of photoenergy. Photooxidation, that is a different story we will discuss, right? Enzymatic oxidation, active oxidation reactions accelerated by certain enzymes. That is not due to the photoenergy or other reasons. Oxidation reactions accelerated. Generally, they accelerate due to different facts. Right? Basically, they accelerated by enzymes in enzymatic oxidation reactions. Right? So we will see very briefly one by one what is photooxidation, what is photooxidation, and what is enzymatic oxidation. Right? First, we will take photooxidation. Right? Actually, photooxidation reactions, that is a chain reaction. Oxidation is a chain reaction. So, therefore, we can identify common steps. Right? Common steps. Common steps mean there are certain common steps, right, common for all type of chain reactions. Right? We can identify certain common steps. Right? So, those common steps are common for all the chain reactions. Those reactions are initiation reaction, then propagation set of reaction. Next one is termination reaction. So any chain reaction we can divide into these three steps. Right? If you take any type of chain reaction, there should be an initiation step or few steps, right? Then propagation steps, right? How to propagate we have to think, right? Then termination. right? What is the end point of this process? So, photo-oxidation is a chain reaction. Therefore, we can identify several different stages of this process. Right? The first important point is generally photo-oxidation undergo with the unsaturated fat. Right? Fatty acid. If the fat contain unsaturated fatty acid, so those kind of fats are very easily undergo photo-oxidation. That is very important fact. Right? That is very important fact. Because in this reaction, as an initial step, formation of free radicals is the very important point. Right? Free radical formation generally start at the double bond position. The double bond position, right? You can observe, right, the formation of free radical as an initiation step of the photo-oxidation. Right? Then gradually formation of double bonds, right, rapidly increase. That is propagation. Right? Due to the formation of free radicals, right, initially different types of free radical, right, among them initials are peroxides, right, peroxy free radicals, because they are very stable compared to alkoxy free radical. Right? There are alkoxy free radical also, right, alkoxy free radicals also, but compared to the peroxy free radical, that is stable. So I think if you have any question regarding the alkoxy and peroxy, it is like this. Peroxy free radical mean we can write like this, ROO dot. Dot indicates single electron. Right? Alkoxy mean this one. Right? CH2. Right? So during the auto-oxidation, actually not methyl, right? Any alkyl group, right, join with oxygen and additional or odd number of oxygen, right, and form alkoxy. Then any peroxy compound can behave like this, right? So this is peroxy radical. This is alkoxy radical. So alkoxy radical, in compared to the stability is very low compared to this one. Therefore, in the initiation level, you can observe formation of more peroxy radical in the system. More peroxy radical in the system. Initially, very small, gradually, amount of peroxy radicals increase. Right? Then, at the end of the process, what will happen? Right? Initial process, formation of free radical, then peroxy radical formation, then termination level. When it comes to the close to the termination level, then the next point is peroxide. Peroxy radical convert into peroxide. So those peroxide degrade into different compounds. So they are alcohols, ether, ketones, like different small molecular weight compounds. Right? Compound with small molecular weight. So actual rancid flavor generated by those compounds, combination of those compounds. Right? So that means, what can you say about peroxide concentration, right, during the reaction? During the reaction. That means, if you think about the oxidation process, right, when it starts, based on this logic, free radical formation starts. Right? When free radical formation starts, right, most common free radical is peroxy free radical because of its stability. Right? Then gradually it's propagate like this formation of more and more free radicals. And then it comes to the terminal position. Peroxides are the final products. At the terminal position, all the peroxides degrade into small compounds which contain low molecular weight. So those are alcohols, ether, aldehydes like ketones like alcohol. So actual flavor, rancid flavor is due to these compounds. That is very important point. So that means if you try to analyze certain sample, for example, if you take biscuit sample, packet of biscuit, now if you really need to analyze shelf life of this sample, right? So peroxide value is a very important value, right, in the determination of shelf life of the product. So therefore, we have to analyze the peroxide value. We have to analyze the peroxide value of that product, right? Based on that, we can comment so many things, right? To do it, so what are the steps? The steps are, first we have to take a sample, right? If you take biscuit as a sample directly, right? Sometimes you cannot get a very important point. Why? Generally, manufacturers use antioxidants to protect the product from the oxidation process. Therefore, if there is a very good antioxidant, you cannot obtain peroxides through biscuit, right? But if there is a loophole anywhere at the process, peroxide formation can be happen, but not very high quantities, very minute quantities. Therefore, normal titrimetric method you cannot apply for that. Sometimes you have to use spectroscopic method, or sometimes you can use GCMS like to identify the peroxide, because method should be more sensitive, more accurate to determine that value, because the amount is very minute amount. The amount is very minute amount. Therefore, you have to use very accurate, sensitive method. For titrimetric method, you cannot use for that. For general peroxide content, that is, the content is very large, right? Then you can use titrimetric method. But here you can't use titrimetric method because that is not good for this. Sometimes if you try to analyze this sample using normal titrimetric method, right, you may get zero results. Then you may comment sometime the sample does not contain peroxide. So that is wrong. Therefore, especially analysis like things, right? We have to think about that too. Sometimes your sample, right, become negative because of the sensitivity of your method, right? Because of the sensitivity. That means your method, sensitivity of your method, not enough to analyze that amount, right? Therefore, we have to change the methods. Don't rely on one method, right? Depending on the sensitivity, you have to apply few methods to analyze the same compound. Then you can obtain accurate results. So when we discuss food analysis in third year, you can learn that kind of thing in detail, right? Until that, you have to keep all this in your mind. If you try to analyze peroxide content using titrimetric method, biscuit-like sample, you cannot get the correct, accurate results because that method is not sensitive, right? If the people try to do the analysis using DCMS analysis, that is good. But you have to obtain the sample not from the biscuit, right? You have to obtain the sample using syringe as a headspace sample. This is the sample, headspace sample. Headspace sample. That means you have a packet of visitor like this. Packet is sealed, right? Up to this level, I think there is a distance. This area is empty area. Empty area. Then you can insert the needle, syringe, right? Gas empty area. Then take the gas sample out from this packet and inject it to the DCMS column. DC column. Then sample is there. This is headspace sample, right? Sample is there. Now you can analyze based on the suitable solvent systems, right? That is the analytical technique, right? Then, so those things we can discuss under good analysis. So we can't discuss that all these things within first year because we have to cover other parts also. Now you are in first year, you can't discuss this kind of method, right? Therefore, now for your knowledge, for your information, please keep this in your mind. So we can analyze that's very minute amount, very accurately using this kind of technique. Right. Then my question is, if we analyze the sample using this kind of technique, right? If you obtain the result like this, very minute amount of peroxide available. Right? If the result says very minute amount of peroxide available in the sample, so what do you do? What is the option? Option is very important because based on that results, you have to comment it. Sometimes you may be the legally authorized person, not for the general shelf life determination of product development. Right? Sometimes very reputed sample from very reputed company, right? PHI can collect those samples and send to your office. You are the legal officer. So you have the responsibility to analyze and comment. Right? Analyze and comment. So if you obtain the results like this, the product contains low amount of peroxide. What is your comment? What is your comment? Because in the oxidation process, I explained what are the principal steps? Formation of peroxides, then gradually form peroxides, large quantities, then degradation of compound and formation of aldehydes, ketone, alcohols, ethers like compound. Right? So this is the process, very briefly, of oxidation process. Right? If you obtain very minute amount of peroxide, you can't say this product is at the initial stage of the oxidation. You can't say. Why? What is the reason? Sometimes this product may be at the terminal step, close to the terminal step. Why? At the terminal step, what will happen? Peroxide convert into small molecular weight, low molecular weight compounds. Right? At the terminal step, peroxides convert into low molecular weight compound. Therefore, low quantities of low peroxide weight, right? It can have a possibility, right? Like that. Right? Not only that, sometimes you may correct. Because at the very initial stage, peroxide content is very low. Therefore, your comment like this, it should like this, right? This can be initial low, terminal level of the oxidation. Either initial low, terminal. You can't completely say because then further analysis if you obtain aldehyde, ketones, ethers, esters like compounds, right? Then you can say definitely this is the last stage, close to the last stage. Because initial stage you cannot find ethers, ketones, aldehydes like All these compounds you can find at the terminal portion of the oxidation process. Therefore, you have to, if you really need to confirm the step, you have to do the second analysis to confirm it. Like initially, you can say, yes, there is the oxidation process, right? Oxidation process. This can be either initial step, close to initial step, or terminal step. That kind of thing you can. So that's why this knowledge is very important, right? That's why this knowledge is very important. So sometimes, in certain cases, you have to go to the court as a consultant, right? When you work in a certain company, quality assurance manager or chief production officer like position, right? So sometimes certain consumers, right, based on certain qualities of the product, complain, right? Then when they go to the court, right, then court give the message to the company, right? The company should defend the case. The company owner select sometimes you, because you are the person responsible for that part, right? Then court may ask questions regarding the oxidation. So you have to have an ability to explain all oxidation process very clear, right? That's why you learn this kind of thing. That is the importance of these points. Sometimes you may think, what is the importance of this oxidation? Like it could be no rancid flavor, rancid compounds and everything. That is enough. But other importance of this? This is an important point. One day you will become a food scientist, food technologist, responsible persons of this country, right? Then you have to have a responsibility to protect consumers from others, producers, right? Illegal products, right? That is your duty, because we are learning under free education environment, right? More taxpayers, more Sri Lankans, right? Allocate large quantity of money for that. Therefore, that is our responsibility. Please learn thoroughly regarding this kind of matters, right? Right. Then, with example, we will see what is auto-oxidation. Using example, we will see what is auto-oxidation, right? Right. I will take this example. CH3, CH2 6 times, CH2, CH, double one CH, CH2, CH2 6 times, COOH. This is the example. Right? This is the example. Right? Before we discuss the example, we should know there are certain important things regarding the auto-oxidation. Auto-oxidation, I explained, initial starting point is double bond, right? So formation of free radical, right? Starting point is the double bond. Therefore, this is 100% related with the unsaturated compounds, right? This initial step, starting time, is very important for this reaction. That is the bottleneck of the reaction, right? This time is known as induction period. It's a period. Induction. So induction period means time required to initiate the oxidation reaction. Time required to initiate the oxidation reaction, that is induction period. Right. Within the induction period, reaction can start. So induction period of the reaction vary with compound to compound. The induction period vary with compound to compound. If I take two examples, oleic acid. Oleic. Right? This is oleic acid. We look example, oleic acid. Right? Induction period. Induction period 82 hours. Right? Oleic acid, induction period 82 hours. But if we take linoleic acid, induction period 19 hours. Compared to oleic, very low. Compared to oleic, very low amount of induction period. Then linoleic acid, induction period 1.3 hours. It is less than 2 hours. All these hours. Very big difference. Very big variance. You can obtain. Then if you check the number of double bond available in this compound, oleic double bond 1, linoleic 2 double bonds, linolenic double bonds. In our first session, we discussed these are essential fatty acids, right? Essential fatty acids. There are number of food material, right? Those food material contain linoleic, oleic-like compounds, fatty acids, right? Out of these, all these are unsaturated. Therefore, all three types can undergo oxidation process, right? Oxidation process. Compared to the induction time, highest induction time, oleic, then linoleic, then linoleic. The lowest time is linoleic, right? When you increase the degree of unsaturation, right? When we increase the degree of unsaturation, what will happen? Induction time decrease. That means this kind of relations, right? Degree of unsaturation proportional to 1 over induction time. Degree of unsaturation equal to, sorry, not equal to, is proportional to 1 over induction time. That is a combination. That is the relationship between induction time and degree of unsaturation. Therefore, if you take monounsaturated fatty acid and polyunsaturated fatty acid, polyunsaturated fatty acids are more tend to oxidize rather than monounsaturated fatty acid. So if we take saturated fatty acid, right, we don't worry about auto-oxidation. But there are other types of oxidation, but we don't worry about auto-oxidation. Because auto-oxidation process principle behind that is formation of free radicals at the double bond position. Saturated with no double bonds, no auto-oxidation process. Right? Therefore, we can neglect it. But if it is unsaturated, remember, right, depending on the degree of unsaturation, induction time gradually change. Right? Then, in addition to that, there are certain additional factors which are accelerate this process. Accelerate. Those are heavy metals like. If you take heavy metals, these are very dangerous things with respect to this kind of oxidation. Right? Not only that, certain environmental factors, moisture and wind, right, support for this oxidation. Right? Like these factors, very important. Temperature, environmental factors are very important for this oxidation. Right? If it is optimum, right, optimum rate of reaction you can observe. Right? Optimum rate of reaction you can observe. Right? Then we will go with the examples. Right? Initially, to identify the compounds, we can number the carbon. To identify the compounds, we can give the numbers to the carbon atoms available in the compound. Right? Based on numbering, this is 8. Because up to this 7, 8, 9, 10, 11. Right? Because I am following chemistry numbering system, impact numbering system, or UPSC numbering system, not the physiology system. Right? Therefore, I start the numbering from this side. So, as last session, we explained we can number this kind of compound in both ways. But IUPAC regulation, right? I can select the highest active group. Therefore, we can start the numbering from this. Right? Based on that, this carbon is 8. This is 9. This is 10, 11. So there is a double bond between 9 and 10. 9 and 10. Right? So the reaction start at this position. Reaction start at this position, right? Because of this double bond, right? Because of this double bond means if you take 2 carbons, right? What is double bond? One bond is a sigma bond. Other one bond is a pi bond. Right? In chemistry, in organic chemistry, you may learn this theory. If you take a double bond, one is a sigma, other one is a pi bond. Right? Then pi bond due to the pi electron cloud. That is due to this kind of thing. You take 2 carbon, in the pi electron cloud. Attraction of pi electron clouds form pi bonds. That is the theory behind the double bond formation. Right? Therefore, this attraction may affect to the closer carbon source. This attraction, this double bond may affect to the other carbons, close to the carbons. Right? Therefore, initial step, hydrogen released from the 11th carbon, if you take this one, right, as a peroxide. Sorry, free radical. Right. You can select this one also, right? 8th one. Now here I am going to select 11th one. Same thing you can draw with the 8th one. Same thing you can draw with the 8th carbon. But here I select 11th one. That is my preference. Right? If you like, you can go with the 8th one or both at the same time. Right? What is the first step? Releasement of the hydrogen attached to the 11th carbon as a free radical. So what is the compound? What is the product? This is my product. Product is this one. CH3, CH2, 6 times. Now this is not a CH2, it is CH. CH, free radical. CH, CH, CH2, CH2 6 times, C double O H. This is the process. Right. Now you can observe free radical as a major product. Right? Free radical goes to the double bond. Therefore, double bond try to absorb this free radical. During this process, due to this attraction, you can observe rearrangement thing within the system without involving external party. You can observe rearrangement within the system. Right? So there is a formation of free radical, right? One electron containing highly reactive component, right? That electron on the 8th carbon, right? But we know, sorry, electron on the 11th carbon, but we know 10 and 9, that is double bond, 10 and 9 double bond, and 5 electron counts is there. Therefore, that cloud try to absorb this one. So what will happen at the end of the process? All molecule rearrange. All molecule rearrange, right? That is without contributing the external party, all molecule rearrange. So what is the product? Due to rearrangement, is the product. Rearrangement we can explain like this kind of half arrows. This kind of half arrows. In both ways, we can explain. Time to time. Time to time, both ways. Right? So this is the product. CH3, CH2, 6 times, this becomes CH. So this becomes CH. The next one becomes CH. CH2, CH2 6 times, C double. Now, if you try to analyze, you try to name these carbons. This is 8, 9, 10, 11. Now, this is 8, 9, 10, 11. What happened? What happened during the rearrangement? During the rearrangement, this free radical electron transferred to the 9th position, right? Then double bond shift to the 10th position. Initially, double bond at the 9, 10. Now the double bond at the 10th level, right? Because of this free radical. But still, this is a free radical. Remember, because we do not give the additional electrons to the system. Therefore, still it is a free radical. Within the system, it's rearranged like this possible structure. Right? Then the next step, this compound interact with oxygen. The next step is compound interact with oxygen and form, right? And form peroxide free radical. That is CH3, CH2, 6 times, CH double bond CH, CH, CH2, CH2 6 times, COOH. Now here O, no. Again free radical, but this is peroxide. Right? This is peroxide. If I number again 8 carbon, 9, 10 and 11. Right? 8, 9, 10 and 11. Same carbon, but the thing is now free radical, right? Free radical at the now free radical at the 9th position. This peroxide free radical can interact with this kind of H dot and form hydroperoxide. Right? When this free radical interact with this one at the terminal position, close to the terminal position, it can form peroxide. So this is the initial compound, peroxide free radical. Right? Then, when it goes to the terminal step, right? What will happen? This peroxide free radical interact with the hydrogen free radical and form peroxide. Right? So this is the things, right? This is the explanation for the 11th position. Right. So if you think about 8th position, then you can think about peroxide at the 10th carbon. If you start with the 8th position, you can think about the 10th carbon. Right. Likewise, there are 4 possibilities. There are 4 possibilities for one double bond. Right? Due to one double bond, there are 4 possibilities. Then I will explain possibilities. Right? Due to one double bond, it can form 9 hydroperoxide. 9 hydroperoxide. This kind of compound. 11 hydroperoxide. 8 hydroperoxide. 10 hydroperoxide. 4 types of combinations can be there. 9 hydroperoxide, 11 hydroperoxide, 8 hydroperoxide, and 10 hydroperoxide. Right? Remember, all the compound contain hydroperoxide radical contain double bond. All the hydroperoxide compound contain double bond. Okay? Double bond. Therefore, in addition to these one, we can identify 2 geometrical isomers, cis and trans. So 9 hydro, to take one type 9 hydroperoxide, there are 2 isomers, cis and trans. Right? Therefore, now up to this level, we have 2 compounds. Although this one group, 2 compounds. Then again, stereochemically, right? There are stereochemical reactions, right? Because of this, because these are 3-dimensional compounds, right? Stereochemically, therefore, you can observe 2 types RS. RNs. All these 1 RNs. Right. Now, how many compounds? Per group, 4 compounds. Right? 9 hydroperoxide, 1, 2, 3, 4. 4 compounds. This is 4. This is 4. This is 4. What is the count? 16 due to 1 double bond. Now you can think about the capacity of double bond. Right? 16 compounds. 16 type of compound due to 1 double bond. Due to 1 double bond. That is very important thing. So if we think about polyunsaturated fatty acid, now you can think, right? Polyunsaturated fatty acid, you can think how many number of peroxide, right? That depends on the options. One group definitely contains 4, right? If the number of options are very large, number of compounds very large, right? Therefore, consumption of the polyunsaturated fatty acid contained in compounds is, right, sometimes dangerous because You have to think about the shelf life and everything before you consume. Right? Because it is very easily undergo auto-oxidation. Right? Now you can identify the reactions and everything. You can understand what is the process, how dangerous the process, right? How dangerous the risk regarding the polyunsaturated fatty acids. But if we take monounsaturated fatty acids, it's 16 compound, 16 type of compounds, right? This is minimized. Right? So that's why you have to select good quality cooking oils, good quality oil sources for the food manufacturing process. Right? So if it is unsaturated, people may think palm oil like this, that is better, just better with respect to this oxidation. With respect to this oxidation, that is better. But there are other types of oxidation. So now we are going to explain. Right? In the next few weeks, right? There are other types of oxidation. With respect to auto-oxidation, palm oil is better than other one. Right? But don't cut that only that part. Don't cut only that part from this session. Right? I can't say palm oil is good. Right? With respect to auto-oxidation process, palm oil is good. That with respect to part is very important part. Right? Then we will see what will happen at the terminal step of this oxidation. This happens the terminal stage of this oxidation. Now we see propagation steps and initial steps. We discuss induction period, right? Relationship between induction period and degree of unsaturation, everything we discuss. Right? Then we will see the terminal step of this reaction. Terminal step of this reaction. So terminal step like this. If you think, if you end this kind of RCHOOH as peroxide, R tags. Very simple. If you think you end with this kind of peroxide compound at the end of the oxidation process, then we will see fate of this compound at the end of the reaction. That is the terminal step of the oxidation. Right? Terminal step. So we will see it can undergo this kind of degradation process. R CHR dash or peroxide can convert into this kind of variant initially. Then, if you really need to form this one, you have to remove hydroxyl as a reader. Right? From this compound, OH as a radical, from this compound, therefore product can be this. Right? Then we think about interaction of this compound with RO free radicals. So this kind of free radicals are available in the system. Different types of free radicals, alkoxy free radicals are available, right? Then what is the compound? Then this can be converted into two types of compound, RCOR or ROH. What are the compounds? Ethers and alcohols. Right? If it can interact with this kind of RO free radicals, right? The compound finally produces ethers and alcohol like this, right? Or if this compound interacts with the hydrogen free radical, this is directly converted to RCH RS OH alcohol, right? And the third next option. If R dot release from this one, final reaction, final product is RCH2 aldehyde. Right? So, ketone, alcohols, and aldehyde. As a terminal oxidation, due to terminal oxidation step, right? Formation of alcohols, aldehyde, and ketone like low molecular weight compound. Initially, we have high molecular weight compound. It's break into smaller compound like this. This is the terminal step of the auto-oxidation. Terminal step of the auto-oxidation. That's why I explained, if you obtain very low amount of peroxide, it can be at this, very close to this step. Right? Not the, sometimes at the initial formation of peroxide at the initial one. That is again very good. Right? Otherwise, you can't say this does not transit. That kind of statement you cannot give. Why? This is the mechanism of the reaction. So you have to think about the mechanism. Then you have to explain everything based on the mechanism of the reaction. Right? So this is the whole reaction of auto-oxidation. If I summarize that part again, auto-oxidation actually affects the unsaturated fatty acid. When we discuss auto-oxidation, we have to discuss it with unsaturated fatty acid, not with the saturated fatty acid. Because basic requirement for the auto-oxidation is double bond, presence of double bond, availability of double bond in the compound. Right? Therefore, at least one double bond should be there to start the reaction. Right? Unsaturated compound. Right? And the second thing, this reaction we can categorize as chain reaction. Therefore, three major steps common for all chain reactions can be identified in this auto-oxidation process. Initiation, propagation, and termination. All three steps we can very clearly identify. For the initiation step, we have to think about the degree of unsaturation of the compound. Because when degree of unsaturation increase, right, time taken for the initiate the reaction decrease. When degree of unsaturation increase, time taken for the initiate the reaction decrease. That is proportion like that. 1 over induction time, degree of unsaturation. So we consider three examples: oleic, linoleic, and linolenic. Right? Oleic, one double bond containing compound; linoleic, two double bond containing compound; linolenic, three double bond containing compound. Gradually, induction time decrease. We can also discuss those examples. Then we move to the mechanism, right? Move to the mechanism. So we discussed the mechanism of the system, initiation, reaction, everything. Then we found actual reason for the reaction. Right? Then we took the example monounsaturated fatty acid, right? And we observe the formation of free radical during the reaction. Right? Then, based on the free radical formation, we can develop the propagation set of reactions. Right? Initially, peroxy free radical form, then peroxide, then when it goes to the terminal step, so those peroxides convert into alcohols, ketones, and aldehydes like low molecular weight compounds. Right? So not only that, if you take the number of compounds formed during the auto-oxidation process, right, per double bond, Actually, we can categorize 4 types based on the 4 carbons per double bond. Right? So one type can produce, because of the final product containing double bond, one product you can develop as a cis and trans geometrical isomers. You can consider not only geometrical but stereoisomers also you can consider RS isomers. In one group you can have 4 compounds. Likewise, 4 groups you can have 16 compounds. Now 16 compounds you can obtain due to one double. So that is the monounsaturated fatty acid. Right? 16 compounds can be formed. So if you think about more than one, that means polyunsaturated fatty acid, you can imagine the risk. You can imagine the risk. Right? When you increase the degree of unsaturation, other part also increase. That is induction time also increase or decrease. Then the rate of initiation is increase. Rate of initiation decrease. Time required for the initial point is decrease. That means rate of initiation increase. Right? Therefore, there is a big risk with the polyunsaturated fatty acid compared to monounsaturated fatty acid. That is the auto-oxidation of lipid. We can identify certain factors which are responsible for the accelerate this reaction: moisture, oxygen, heavy metals like factors. So those are accelerate the rate of auto-oxidation process. Right? So these are the very important facts behind the auto-oxidation process. So you have to prepare your own notes. Right? You have to go through the e-books and certain textbooks. Right? And you can think about the research papers, very good journal, SCI journal papers, right? Based on the auto-oxidation of lipid. Then you can refer all these things and you can prepare your own note. You can critically learn auto-oxidation of lipid. If you have any question, you can contact me through your batch rate. Right? Through your batch rate. Right. Then we will think about the next type of oxidation, that is photo-oxidation. Next oxidation type is photo-oxidation. So photo-oxidation actually start due to photoenergy. Photo-oxidation. Photo-oxidation. So photo-oxidation actually results due to the photoenergy. That is not like photo-oxidation. In photo-oxidation start due to the double bond and other accelerating factors. But photo-oxidation requires photoenergy. Photoenergy. Therefore, in photo-oxidation, we can identify 2 systems. In case of photo-oxidation, we can identify 2 systems. Type 1 and type 2. We can name 2 systems as type 1 and type 2 system. Right? Remember, type 1 and type 2. Type 1, type 2. So we can identify 2 systems. Right? So all these systems are commonly identified as photosensitizers. That is the word. Right? This is type 1 photosensitizers. Photosensitizers. Right? Type 2, the same. Photosensitizer. Photosensitizer. Right? Type 1 and type 2 are photosensitizers. Right? So type 1 the photosensitizers. Type 1 help to absorb photoenergy. Right? That is the function of type 1 compounds. Type 1 compounds help to absorb photoenergy to system. Right? Type 1 sensitizers responsibility is absorb photo energy from the outside to the system. So what are the compounds you can have? Can you do the example? Can you think about the example? Example for photosensitizers. Photosensitizers, what are the examples? Compounds which can absorb the photo energy. Chlorophylls. Very simple in the environment. Chlorophylls. Chlorophylls are very good photosensitizers. Right? And second one also related to that one, pure. Right? I will use the names chlorophylls, pure. So these are the type 1 sensitizers. Remember, chlorophylls and pure are type 1 sensitizers. But type 2 sensitizer not help to absorb the energy. Absorb the energy from the outside. Right? To initiate the reaction, we require type 1 sensitizer. It will help to initiate by absorbing photo energy. But to propagate the reaction, we require type 2. So role of the type 2 sensitizer is the propagation of the reaction. Propagation will support the propagate, continue the reaction. Right? Because this is also chain reaction. This is also chain reaction. We can identify 3 major steps, common steps: initiation, propagation, and termination. To propagate initiate the reaction, we require type 1 photosensitizer, that is chlorophyll, pure like compound. Right? Then the propagation. To propagate the reaction, we require type 2 photosensitizer. So what is type 2 photosensitizer? Here type 2 photosensitizer is the singlet state oxygen. Singlet state oxygen. Singlet state oxygen. I think you may have a problem with this word. What is the meaning of singlet state? You may have heard about different types of oxygen, right? But you may not heard about singlet state oxygen in your first year, especially, right? But I am not going to continue this lecture with quantum mechanics, because quantum mechanics is a very complex field, right? Actually, it is very complex with you, that is, you are a bioscience first year student, right? First year science student in bio, you are came through the bioscience stream, right? Therefore, when we start quantum mechanics like lecture series here, that will be a very big problem. But when you learn chemistry in our chemistry department, right, they will teach quantum mechanics in their third or second year, right? Generally, and you may not learn about the quantum mechanics. Actually, that is theoretical chemistry part, right? With lot of assignments, lot of assumptions, right? Lot of equations, mathematical relationships involved in that process, right? But we need not all and everything to understand singular state. Right? We can just understand what is singular state. If you require, you can write down this part clearly. Now I am going to explain what is singular state here. Right? Try to understand. Right? I am not going to ask any questions or anything at the end of the semester, right? Based on the singular state. Explain the singular state like this, because that is quantum chemistry, right? Why do I explain this in this session? to better understand. For better understanding, you have to know what is singular state. Right? You have to have a brief idea, not the complete idea. Very brief idea. If anyone asks what is the difference between singular state and other state of oxygen, then you have to have a very brief idea, because that is very important thing. Right. I temporarily stop the oxidation, photooxidation at this position. Now, from here, I am going to explain what is singular state. Right? Singular state. Right? You know, oxygen. Right? Oxygen. You know the electron level S and P suborbitals at the last shell. Right? Electrons available in the S and P at the last shell. Right? What is the electron configuration? Now you can write down just electron combination. S and P last shell. So that is actually right. That is actually orbitals. S orbitals complete. Right. That is actually distributed among last electrons among p suborbitals. You know, based on your A-level chemistry knowledge, there are 3 p suborbitals: px, py, p. Right? px, py, p. Right? Then, if you try to fill the electrons, so last shell, you can fill like this: 1, 2, 3, 4, 5. Five p electrons. Right? So you cannot obtain other one. Right? Then, if you obtain energy from outside, to the system, what will happen? These p orbitals divide into 2 groups: px, py here, but it is same. I orbit. High energy orbital. Sorry, this is 2d4. Right? High energy orbitals. Right? Therefore, because oxygen is S2p4. Now we are going to fill the p electrons, because we don't worry about s electrons. That is completely filled. Right? But reactive form, we have to think about the p orbitals. Right? Therefore, if you try to fill the p orbitals, right, based on rule, right, we have to fill like this: 1, 2, 3, 4. Because all the p orbitals are at the same energy level, the normal condition. But the compound absorb energy from outside. What will happen? Those energy level, sub-energy level, divided into 2 categories. 2 energy levels are lower, 1 energy level is little bit high compared to that. px, py lower, p is Then if we try to fill these 5 electrons, 4 electrons to the system, what will happen? What is the spinning action? 1, 2, right? So you can't fill the electrons to this level. Why? Electrons are normal in this system. In certain cases, electron absorb the energy and go to the next energy. But here, due to energy, what happened? Due to energy, is energy levels divided into electrons, not the electrons. Energy levels. Then what will happen? Right? Then electron try to fill this normal electron. Electrons are normal level, right? Normal energy. Fill like this 1, 2. It cannot move the higher level because it does not contain additional energy. Same level electrons. Therefore, again it try to fill here. Right? All 4 electrons fill in Px and Py, not in Pz. Right? If I repeat it again, so final shell electron configuration of the oxygen is 2p4. Final shell electron configuration of the oxygen is 2p4 because it's 6 group element. Right? It's 2p4. So we don't worry about the s electrons. If you try to draw the electron distribution within the p orbitals, we have 3 p orbitals x, y, z with same energy. Therefore, at the normal condition, if you try to fill the electrons to the p orbitals, what will happen? All electrons will like this 1, 2, 3, 4 electrons, only p electrons. Right? Then the second condition, under second condition, what will happen? Due to the additional energy, those energy levels deviate like that. 2 energy levels, Px, Py, lower one, Pz, higher one, because of the additional external force, but not the electrons. All electrons are at the same energy levels, same energy content. Right? Then, after the deviation of these energy levels, if you try to fill the electrons of these energy levels, right, due to high level energy, electron cannot just move to the upper one. It will try to fill into the lowest. Right? Therefore, the result like this, all 4 electrons will Px and Py, not with the Pz. Right? Then, in quantum mechanics, there is a theory for simple equation 2s plus 1 to determine the spin quantum number. Spin quantum number. Spin quantum number, right? We can apply this whole formula 2s plus 1. Right? By applying this small simple formula 2s plus 1, we can determine the spin quantum number of the system. Spin quantum number. Spin quantum number. You don't worry about all these technical terms, right? We are going to just explain what is single state, right? Right. Then you apply 2s plus 1 here. Spin quantum number. S means spin quantum number, right? Then we are going to calculate total spin quantum number for this system, right? S means spin of the electrons. Generally, we can give plus half and minus half. depending on the direction of the half arrow. Depending on the direction of the half arrow, we can give plus half and minus half. So if the direction, we can select that first. If the direction is this side, plus half. Opposite to that side, minus half. That is, we can decide. Right? If you use this kind of key, this side plus half, this side minus half, what is the total S here? Px plus half minus half 0. Right? Px means paired electron. Right? Plus half minus half because this. Oh, sorry. When you draw the paired electron, you have to draw like that. That will upward and downward in the one system. That is 0. Then 2 plus halves. Right? Plus half plus minus half plus half plus half. This is the, you have to find the total. Right? This is the answer. Plus half, answer is 1. Right? No need to complex calculation like this. Plus half minus half 0. Then plus 2 plus halves, right? 1. Here, if you apply 2s plus 1 rule here, 2 into 1 plus 1, what is the answer? 2 into 1 into 1 plus 1, answer is 3. Right? Answer is 3. That means spin number for this system is 3. Right? That is triplet state. We need triplet state. Right? Now you can think about the other system. This one. Plus half minus half 0. Plus half minus half 0. That means S is 0 for this system. After absorption of energy, S is 0 for this system. When S becomes 0, what will happen? 2 into 0 means 0. Right? Therefore, 2s plus 1 equals to 1. Because here S is 0. That is 1. Answer is 1. So this is the singlet. Right. This is the singlet state. I think now you can identify what is singlet state and what is triplet state. What is singlet state and what is triplet state? You can easily identify. Right? In case of triplet state, so it indicates electron distribution in the system. One paired couple, one electrons, right? 2 unpaired oxygen with respect to oxygen in the p orbitals. But if you think about the singlet state, both are paired, but restricted to the px and py, not the pz. Right? So that is the explanation regarding the singlet state. Singlet state. That is the quantum mechanics explanation. Right? So if you think it is too complex, you can forget about it. Right? You can forget about it. But sometimes, right, in future, you may further study regarding this. This may be very important. Rate of reactions and study the rate of photochemical reactions, right? This may be important, right? So if you have this knowledge, brief knowledge about singlet and triplet like this, right? You can learn additional things based on that knowledge. Right? But if you think this is unwanted thing, you can forget about it. Only thing is type 2 sensitizers are single state oxygen. That is, you have to keep in your mind. Right? That is, you have to keep in your mind. But why did I explain this in detail? Right? Without cramming, you can explain the photo-oxidation process if you know the singlet and triplet properly. Without any cramming, you can explain. Right? If you don't know the triplet and singlet, you have to just say single state oxygen type 2 sensitizer. That is enough for the good science. That is enough for the good science, but not enough for the good knowledgeable person. Right? To really improve your knowledge, really think about improve your knowledge based on these facts, right? These follow this kind of learning practices. Right? This is very important. Right? We cannot discard anything. Right? Sometimes it is very close to complex mathematics. You have to learn mathematics too. If you really learn that fact, if it is very close to mathematics, then what we have to do? We have to learn mathematics. That's part of mathematics. Because we need to learn. Learning is a requirement. Right? Therefore, you have to do it properly. Otherwise, you can't learn anything. Right? Because this is not a school. In our presentation, I explained. This is not a school. This is the university. Or you are here to learn so many things in the universe. This is the place for them. Right? Then finally, if you are a good person, you have to create the knowledge. You have to add something to the knowledge. Contribute something from your side. Because nowadays, you are following others' thing. Right? We are thinking about equations, we are thinking about theories, we are thinking about explanations, so many things based on others' finding. Why don't we think like that? Right? If you think very properly, why don't we create something? Why don't we add something to the knowledge? Why don't you check others' finding, whether it is correct? What are the factors? Right? Why don't you think about it in a different way? Right? That is very important. That is the learning behavior of the university. Right? That is the difference between university and your school. In your school, there is a teacher guide, and teacher is there. He or she will give the note, right? Based on that note, based on the teacher guide, certain group of people set the paper, right? ECA paper. Then, based on the paper, they are going to evaluate you, and based on your result score, right? You are selected for this course. That is the process. Up to this, that is okay. That is okay. Because before you create something, you have to think about the platform also. Without knowing the platform, you cannot think outside. Right? If you don't have enough knowledge for the current knowledge, regarding the current knowledge, if you don't have enough knowledge, you cannot go beyond that. If you really go beyond that, you have to have proper knowledge regarding current knowledge, regarding that matter. To understand that properly, these kind of evidence are very important. Therefore, don't discard that kind of thing, right? Just because of quantum-like words, right? Quantum is very simple actually. I am also a bioscience student. I was from bioscience student. Right? Learn quantum mechanics, advanced and simple. Both are. That is not easy one, but we face that. After facing, now we know there is a thing. So during those days, right, we learned about one-dimensional box also. Can you believe it? Can you think one-dimensional box? Right? Particle in one-dimensional box. Right? Based on that, we prove certain wave equations. Right? In our O level or A level, we did not learn higher mathematics. But at this university, with the sixth path, we learn to understand that condition, that system. So that is the thing. Right? If you are a food science student, sometimes you may miss that course unit from the chemistry department because we select certain course unit for you from the chemistry department. Right? Among these course unit, I think there are no quantum mechanics like course unit. Right? But when we explain this kind of thing, I also try to contribute chemistry background of all these things. That is very important. That is the difference between the food science and technology degree program, Japura and other ones, STP and other ones. Right? We are in the strong chemistry platform. Strong chemistry platform. Therefore, you can learn so many things very clearly, very competitively. You can create very high quality knowledge to the future. Right? Right. Then, if we think about the process, our process, oxidation process, now you know what is type 2 sensitizer, that is single state oxygen. We explain what is single state oxygen. Right? Right. Then we will think about the reaction. Generally, we can draw the reaction like this. Generally, we can draw the reaction like this. Sensitizer. This is type 1. Type 1. Right? Type 1 sensitizer. Right? Now we know what are type 1 sensitizers, chlorophylls, pure like compound. Right? Type 1 sensitizer absorb the photo energy. Photo energy. H mu. Why do we select H mu for the photo energy? We know the Einstein equation E equals H. Right? Therefore, we generally symbolize H mu as the photo energy. H mu as the photo energy. Right? Because of the energy absorption, this sensitizer become high energy compound. This sensitizer become high energy compound. Right? Can you try to understand this step? Initially, there is a type 1 sensitizer. Right? I explained what are the examples of type 1 sensitizers. Chlorophylls, pure like compounds. Then those type 1 sensitizers absorb photo energy from the surrounding environment. Absorb photo energy from the surrounding environment and become high energy compound. Is star. High energy compound. Then the normal oxygen triplet state. So how do you mention triplet and single state? Using symbol. So triplet state oxygen generally we mention like this. 3O. Single state, this is triplet state. Single state oxygen generally 1. Here we mention the spin quantum number, not the molecular weight. Generally, we use the molecular weight here, right? But now we are going to use spin quantum number. That's why we put this kind of pattern. This kind of pattern. 1, 2, 3, right? Therefore, now here you can draw the different state oxygen, symbolize like this. Green, orange. Right. Then, what will happen to next thing? S star or high energy compound transmit the energy to the different state oxygen. High energy compound, that is S star, type 1 high energy compound, transmit the energy to the triplet state oxygen. Triplet state oxygen. Right. So what will happen? S star become normal S because energy complete transfer to the oxygen. But oxygen becomes single state. Right? Oxygen becomes single state. Right? So if I repeat the process from the initial point, right? There are type 1 and type 2 sensitizers. We discussed about it in the photo oxidation, that these are the very important things. Right? Type 1 sensitizers are photo energy absorbed. Right? So we discuss example chlorophyll, spirophytin type compounds. Right? Then this type 1 sensitizer absorb the photo energy from the outside and convert into high energy compound. That is the first step. Then the next step is high energy, right, try to transmit to the triplet state oxygen, normal oxygen. Spin quantum number of this oxygen is 3. Triplet state oxygen. Right. Then triplet state oxygen absorb this energy. Because of this absorbance, right, absorption, this S star converted to normal S because all the energy transmit to the triplet state oxygen. Right. Then, because of the energy absorption, we explained earlier, triplet state converted to singlet state. Right. Triplet state converted to how? Triplet state converted to singlet state. After energy absorption, energy level divide into higher and lower. Right? Then lower energy levels filled by the electrons. All 4 electrons in lower energy levels, all are paired, they are to single state. Right? So this is the product, single state oxygen. Single state oxygen. Now this single state oxygen interact with the organic compound and form peroxide. Understood? Did you get the point? Right? Everything is very clear, I think. Right? Everything's are very clear. Once the single state oxygen form, it can easily join with the fatty acid, right? And attack the fatty acid and form peroxide. Again, formation of peroxide is there. Formation of peroxide is there. Initiation reaction like that. The earlier case, initiation reaction, formation of free radicals due to double bond. Here, no need double bond. No need double bond. Here, formation of peroxide due to single state oxygen, and it can interact with the fatty acid. Right? That is the reason. Right? Therefore, photo-oxidation is very dangerous. Photo-oxidation is very dangerous. Why? So we can protect so many factors, but protection of food from light is very important. Because you know, sometimes when you go to the market, There are certain oil-based products freely available at the open places. Freely available at the open places. Sometimes certain oils, cooking oils, packed in transparent bottles. Transparent bottles. Now, with respect to this type of oxidation, what you can think? That is not good. Why? When you expose the product to the photo energy, this kind of oxidation reaction can be started. When you expose the product to the photo energy, this kind of reaction can be started. Finally, it can start the photo oxidation. Finally, it can produce the peroxide. Right? So that's why most of the food manufacturers, reputed manufacturers, they use dark environment, dark packaging materials to cover their product. That is the reason. So when you select packaging material for the product, you have to think about that. When you select packaging material for the product, you have to think about this factor also. To protect the food from photo oxidation, you have to think about the quality of the packaging material like this. Right? Then other important thing we discuss, general discussion, we discuss heavy metals, support for the free radical formation. Not only photo oxidation, right? Photo oxidation also same. Heavy metals are supportive thing. They are catalysts. Then we will see how heavy metals work as catalysts in this process. Right? For example, if we say capital M symbolize heavy metals. Heavy metal contain large number of electrons, Mn plus. Mn plus. Mn plus means ions, metal ions. Interact with peroxide. What will happen? When heavy metal interact with peroxide, it can form M N plus N, 1 N plus 1 plus RO plus OH. That is first reaction. Then again this one, Mn1 plus. One plus interact with the second peroxide. RO2 plus H plus again the formation of Mn plus. Now you can think. Initially, there is a formation of Mn plus due to the heavy metal. If heavy metals are there, you can observe the formation of this ion. Right? Then there is a peroxide in the system. If it is the oxidation reaction, right? There is a peroxide oxidation. Peroxide is a byproduct. Then these metal ions interact with peroxide. Metal ion easily interact with peroxide. So what will happen? It can form Mn plus 1 plus. Right? It will give the electrons. And it can break the compound into RO plus plus OH minus. RO plus OH minus. Then again that heavy metal ion interact with second peroxide molecule, fresh peroxide molecule, and O RO2 plus H plus, right? And Mn plus. Mn plus means original one. Now you can observe. This is like a cycle. So one heavy metal present, at least one heavy metal ion atom present, right? Cycle can start like this. So like this reaction, heavy metal can accelerate the oxidation. If anyone need to prove that, right, you can explain using this equation. How heavy metals accelerate the system, you can explain it. Right? You can explain it. It's the system. Right? Right. That is about the photo-oxidation, right? Then we will think about the photo-oxidation. Sorry, enzymatic oxidation. Enzymatic oxidation. Third oxidation type. Enzymatic oxidation. Enzymatic oxidation. Here, oxidation process catalyzed by the enzymes. In this type of oxidation reaction, oxidation process catalyzed by the enzyme. Most important things are what are the enzymes responsible for this process. There are few groups. I will explain two major groups. One group is lipases. Other group is lipoxygenases. Two groups responsible for this oxidation, lipase and lipoxygenase. Lipase and lipoxygenase, these are the responsible group of enzymes. Right? So what is the reaction? This is not a chain reaction. It is not a chain reaction. Right? When enzyme interact with the ester linkage, because we know fats are esters, ester linkage, very easily ester break into two compounds. One is a glycerol, other one is a fatty acid. Right? That means last session I explained what is fat. Fat is ester. Two components available in the ester, acid part and the alcohol part. Alcohol part of the fat is glycerol. Acid part is the fatty acid. So that when that bond break by enzyme, right, what will happen? Two products release. One product is the fatty acid, other product is the glycerol. But you cannot detect the glycerol level, you can detect fatty acid level as a free acid. Therefore, if you really need to analyze enzymatic oxidation of the fat, you have to analyze the free fatty acid content of the food fatty. Free fatty acid content is the value. Free fatty acid content. Right? If you really need to analyze the fatty food, fat-containing food, you have to analyze the free fatty acid content of the sample. It says freshness of the sample. Freshness of the sample. If it is full fresh food, this content is very low. This content is very low. But if it undergo enzymatic oxidation, due to that enzymatic oxidation process, right, formation of free fatty acid, you can observe therefore free fatty acid level is very high. Level is very high. Right? That is enzymatic oxidation. Then we will think about how do we prevent oxidation reaction process. Oxidation is not a good process, positive process for the food. It is bad process with respect to the shelf life of the food. Right? Therefore, we have to protect food from oxidation reaction. Right? So, how do you do it? To do it, we can apply antioxidant. Anyhow, we have to stop. We have to stop the chain reaction. If we can stop the chain reaction, so we can control the reaction. If we cannot stop the chain reaction, we cannot control the reaction. That is very important thing. Right? That is very important. First two types of oxidation, photo-oxidation and photo-oxidation. In both cases, we have to stop the chain reaction because both types based on the chain reaction. But last one, enzymatic oxidation, not the chain reaction. Right? That is different approach we can follow. But for the first two types, definitely we have to stop the reaction by stopping the formation of free radicals. So how do you stop reaction for those things? That is photo and photo-oxidation systems. We have to apply certain compounds to control the formation of free radicals. To control the photo-oxidation and photo-oxidation, we have to add certain compounds to the system to control the formation of free radical in the system. To control the formation of free radical in the system. To control the formation of free radical in the system is very easy thing. Very easy thing. We can select certain group of compounds for that. Those compounds are identified as antioxidant. Those compounds are identified as antioxidant. Antioxidants. Right. So we can use antioxidants. We can use antioxidants to control the system. Antioxidants to control the system. Remember this. Right. Right. These are antioxidants. Antioxidants. So antioxidant can absorb the high reactive electrons from the free radical and it can stop the reaction. Right? It has an ability to absorb the high reactive electrons. Otherwise, it cannot behave as an antioxidant. If you select any compound as antioxidant, that compound should have a capacity to identify the highly reactive electron from the system. Right? Otherwise, it cannot behave as an antioxidant. Right? So there are certain antioxidants. Some are not real antioxidant. Some are not real antioxidant. Right? Therefore, we can identify three categories. Some are not antioxidant, but will help to retard the rate of reaction. That is, process is like the antioxidation like process. Right? Oxidation process, and opposite to that, that is antioxidation. Oxidation is this way, antioxidant is the opposite way. Right? Now we are trying to stop the oxidation. That is antioxidation process. Right? There are few ways, few types of compounds help to antioxidation. The first type of compound which are not real electron absorbers. Which are not real electron absorbers, but it can control the activity of transient metal line, heavy metal line. Right? They are not real electron absorbers, right? But it can very easily control the heavy metal line. Control the heavy metal line by chelating them. Chelating means it can form bonds with the heavy metal. Heavy metal line compounds are citric acid, phosphoric acid, citric acid, phosphoric acid like compounds which can easily form bonds with the metal line. But after formation of bonds with the metal line is not available freely to accelerate the reaction. Right? It is not available freely to accelerate the reaction. That is very important point. But we can't say metal line absorb the electrons. Therefore, this is first category. First category of antioxidant like this. Second category, actual natural antioxidant. Natural antioxidants. What are natural antioxidants? So when we learn so many things, phytochemicals and so many things, we can say we have our food contain lot of antioxidants. Plant sources contain lot of antioxidants. Right? So what are natural antioxidants? If anyone asks a question, right? People have few answers. Right? People have few, but we have so many compounds which can behave as natural antioxidants. Right? So most of the natural antioxidants contain very important part in their structure. Most of the antioxidants contain very important chemical part in their structure. That is phenolic group. Most of the natural antioxidants contain phenolic group. Phenolic group in their structure. Can you tell me the very famous natural antioxidant? Very famous natural antioxidant available in the system. Can you think now? Yes. Very famous antioxidant is a vitamin E. Right? Chemical name is the alpha tocopherol. Alpha tocopherol. Alpha tocopherol is the vitamin E. Vitamin E is the alpha tocopherol. Right? This is the famous antioxidant, natural antioxidant available in coconut oil like natural system, very famous. In addition to that, certain carotenoid compounds, beta carotene like this. Carotenoid compound contain phenolic group. Right? Phenolic group. Most of the phenolic compound available in plant sources, right, have an ability to absorb the electron, therefore they can act as antioxidant. That's why doctors advise to the people consume plant sources to control the cancer-like condition. Cancer condition related to the reaction between certain biochemical reaction between that kind of free radicals. There is a relation in that series of biochemical reactions, right? To control, if you can control the free radical content of your body, you can minimize the risk of cancer. But how do you minimize the risk of free radicals? You have to consume more antioxidants, natural antioxidants. How do you consume more natural antioxidants? You have to consume more plant sources. Most of the plant sources contain number of phenolic compound, all these are antioxidants. Now we will see. So that is the theory. Theory means phenolic compound can act as an antioxidant. Right? This is theory. But how do you do it? By using structure. By using the structure of the antioxidant, how do you do it? That is very important. That is very important. That is the difference between our lecture series with others. Right? Our lecture series, we explained certain facts with the reasons. Right? If anyone required to learn what are the antioxidants, these are the antioxidants, phenolic compounds are antioxidants, you can list out like that. Right? Then at the end of the process, if anyone asks what is antioxidant, you can very nicely explain these antioxidants, these are the examples of the antioxidant like this, right? If anyone asks a question again, how do you prove this? How phenolic compound acts as an antioxidant? Then you have to give the explanation like this. Now we are going to prove how phenolic compound acts as an antioxidant, right? By using phenolic structure. Right? General chemistry, very simple chemistry is important for this explanation. We know phenol, like is the structure, right? All agree with me. Phenol structure, it is simple structure, right? Then do you know the Kekulé structures of benzene? Kekulé structures of benzene, Kekulé structure, right? Although we draw this kind of bonds, generally we believe that there is an electron cloud within this ring. Aromatic compound, there is an electron cloud within this ring. Therefore, time to time, places of this bond can be changed. Time to time, the places of bond, double bonds can be changed. Right? It is like this. Initially, this hydrogen released as H plus and give the electrons to the oxygen. Hydrogen released as H plus and give the electrons to the oxygen. What is the product? Product like this. Phenate ion. Product is the phenate ion. O minus. This is the product. Phenate ion. Then next step, this electron is the minus charge. This electron due to CO bond. Right? When it comes to the CO bond, this bond should be break and give the electrons to this one. Both the positions. Right? The next structure like this. Oxygen, electron density high here, Then what happened? This electron come to this port, and this port break and the electron. Next structure. Double bond, right? Now here, what? But this point negative. Next structure. Right? This port is same, but here this electron fused to this port and this port break. Now the bond is here. Then go to the next part. This port formation here. Again, this electron goes to oxygen. Now the period time reform with this right. Then as the next step, join with the hydrogen again, formation of ketone can be happen. But with different electron configurations. What are these structures up to this level? Up to this level, from phenate ion, what are these structures? What is the name for these structures? I think you know the singular name. As the spheres, you know the singular name. But the technical terms for these structures are resonance structures. Resonance. Resonance structures. Okay, single samprayukta view. But herein after, don't try to use that kind of terminology because you have to refer so many textbooks in English, right? Therefore, try to follow this terminology. These structures are resonance structures. So by using resonance structures, now you can prove the capacity of phenol as electron absorption. Capacity of phenol as electron absorption. Once it absorbs the electron, it can delocalize. This process is known as delocalization. Delocalization. Right? Once electron absorbed to the system can delocalize the electron. Right? Share the electron within the electron cloud. Share the electron within the electron cloud. Right? That is the delocalization. So delocalization process help to right control the free radical. So free radical contain additional electrons. So phenol-like compound absorb those additional electrons and delocalize that electron throughout the electron cloud. Right? Delocalize the electron throughout the electron cloud. Right? And through the resonance structures, therefore, you can minimize the oxidation process. No more antioxidant. Because all the additional electrons available at the free radicals absorbed by the phenol. Absorbed by the phenol. No more additional electrons. Therefore, you can very nicely control the oxidation reaction by using this kind of antioxidant. This kind of antioxidant. Right? Examples, different types of plant material. Very basic example is a vitamin E, alpha tocopherol, I explained it. Right? Then other important part is the carotenoid compound. Carotenoid compound contain again phenolic group. Then it can. Right? Other important thing is exceptional role of the carotenoid compound. That is photooxidation. With respect to photo oxidation. Right? It's act as free radical absorbent as well as other role, not in the photo oxidation. In case of photo oxidation process, carotenoid compound try to reabsorb energy from singlet state oxygen. That is important fact. Carotenoid compound try to reabsorb energy from singlet state oxygen. If there is a singlet state oxygen, in the system, the reaction continues. Singlet state oxygen joined with the compounds or peroxide. Continuously it will do. Right? But anyone try to absorb the energy from singlet state oxygen, again it converted to crystal. Anyone try to absorb energy from the singlet state oxygen, it will convert into singlet. Singlet state will normal oxygen. Right? Then normal oxygen cannot interact with the compound like that. Then you can control the photo oxidation also. Right? With respect to the photo oxidation, remember, carotenoid play a very important role. Right? With respect to the photo and photo oxidation, phenolic compound has certain carotenoids, which contain phenolic group, play an important role because of the phenolic. With respect to the photo and photo oxidation, with respect to the photo oxidation, they will play an important role. But especially, if you really need to control the photo oxidation, what are the compounds? Compounds are carotenoids. Why? You cannot control phenolic. You can control photo oxidation by using phenol. There are no that kind of free radicals. There are no that kind. But formation of singlet state oxygen is a problem in that system, not the free radical. Formation of singlet state oxygen is the problem in that system. But photo oxidation, formation of free radical is the problem. It is two systems. Therefore, you have to identify the reason with respect to the process. Right? If anyone asks to control the system, so you have to think what kind of process is there. Whether it is photo oxidation, you have to go with the carotenoid like compound. Right? If it is photo oxidation, you have to go with the phenolic type antioxidant. Remember, that is very important when you select the antioxidant for the controlling process. Right? So, how do you control the enzymatic oxidation? That is very simple. To control the enzymatic oxidation, we have to inhibit the enzyme. How do you inhibit the enzyme activity? We have to increase the temperature of the system. When you increase the temperature of the system, you can destroy the enzyme. When you increase the temperature of the system, you can destroy the enzyme. Then you can control the enzymatic oxidation. Now we have already discussed three types of oxidation: photooxidation, enzymatic oxidation. What is photooxidation? We discussed it very clearly. Photooxidation means oxidation of fat due to the double bonds, right? Due to the double bonds. It is a chain reaction. It consists of three main common steps: initiation, propagation, and termination steps. Then if we take initiation step, that is the formation of free radicals and formation of peroxide. Propagation gradually forms the peroxide. And termination, when it goes to the termination step, it will stop the reaction by forming low molecular weight compound. Then if we come to the photooxidation, that is totally different from the earlier mechanism. Responsible ones are categorized into two groups, type 1 and type 2 sensitizers. Type 1 and type 2 sensitizers. So type 1 sensitizer means photo energy absorption. Type 1 sensitizers are photo energy absorbent. Type 2 sensitizers are single state oxygen. Right? Type 1 sensitizer is the photo energy absorbent. Type 2 sensitizer is the single state oxygen. So, oxygen generally energy absorbed by the type 1 sensitizer. If we take, I give the symbol capital S for that. Type 1 sensitizer absorb the energy and go to the high energy level, right? Then it try to transmit the energy to the triplet state oxygen. Freely available type is triplet state. So triplet state oxygen absorb that energy from the type 1 sensitizer, then it becomes single state. So I explained in the meantime what is single and what is triplet. I am not going to re-explain it. Right? If you have any questions, you can contact me through your batch script. Right? I can further explain to you. Right? But don't worry about the quantum mechanics part. Triplet state oxygen convert into single state after absorption of energy from type 1. Right? Then it will convert into single state oxygen. Right? Then single state oxygen attach to the fatty acid molecule and form the peroxide. Peroxide formation you can observe like that in the photo-oxidation process. Right? Then process is same as the terminal step. It is again chain reaction. Initiation is step is formation of single state oxygen. Propagation steps are formation of peroxide as same as the photo-oxidation, and termination is formation of aldehyde, ketone, alcohol like this, right? As same as the photo-oxidation, right? That is photo-oxidation. The third type of oxidation we discussed. Third type of oxidation is the enzymatic oxidation. Enzymatic oxidation is actually catalyzed by the enzyme. Two types of enzymes we discussed. That is, two types of enzymes are lipases and lipoxygenases. Lipases and lipoxygenases enzymes involved in this enzymatic oxidation process. How do we think about the process? This is not the chain reaction. This is normal enzyme catalyst reaction. So, if you really need to explain enzymatic oxidation process, fat is an ester. We can categorize it as an ester. So, if you take this ester, when ester linkage break, right, it will result the original component fatty acid and glycerol. Fatty acid and glycerol. Right? Therefore, when enzymatic oxidation in progress, what will happen as a result of enzymatic oxidation? You can observe formation of free fatty acid in the system. So, if you analyze the free fatty acid content of the system, if it is very high, now it indicates there is a process like that, that is enzymatic oxidation. That is the thing. Right? Then we think about the factors, right? Very important factors, heavy metal to catalyze those reactions, especially first two types of reaction, photo and photo-oxidation. Heavy metals support to give the electrons to the peroxide, interact with the peroxide, and form more ionized form. Then again, this more ionized form interact the second molecule of peroxide. We explain everything on the board, right? And form another type, right? Again and again, form more ionized form of the metal. It is again cycle. It's again cycle. Therefore, increase the rate of oxidation. Then we think about how to control this reaction. There are few control measures. We categorize controlling systems, antioxidant system, into three categories. First category, they are not real electron absorbent, but they can control the activity of heavy metals by forming chelating bond. By forming chelating bond, they can control the activity of heavy metals. Right? when they bond with the heavy metals cannot interact with the others. Therefore, it cannot accelerate the rate of the reaction of the fat oxidation. Right? That is first category. The second category of antioxidant, actually natural antioxidant. Most of natural antioxidants are phenolic compounds. Most of natural antioxidants are phenolic compounds. Among them, the very common antioxidant is the natural antioxidant, vitamin E, alpha tocopherol. Alpha tocopherol is a very common antioxidant available in the system. In addition to that, there are phenolic compound. That's why people are advised to consume more plant sources, because more plant sources mean more phenolic compound you can obtain from them. Because most of the cancer cells development related biochemical reaction based on the free radicals. Based on the free radicals, to control the free radical activity, you can consume more phenolic compound containing food. So that's why it is advisable, right? Then if we think about carotenoid part, that is very important to control the photoxidation. When we think about photoxidation, we can't control photoxidation by using phenolic compound. Phenolic compound used generally for the photooxidation. The photooxidation, we need to control the singlet state oxygen formation. How do we protect the formation of singlet? Rotation of formation of singlet state oxygen. So we have to use carotenoid-like group, carotenoid compound, so that carotenoid can absorb the singlet state energy from the singlet state oxygen, then because of that absorption, singlet state oxygen again go back to the singlet state. You know, when we start photooxidation, we explain type 1 sensitizer, absorb the energy, then it transfers the energy to triplet, then triplet convert into singlet. Now here, backward reaction like this, come to the carotenoid, come to the picture, absorb energy from the singlet state, then it goes back to the triplet state. Triplet state is not harmful thing, then you can protect the food from the photooxidation. Right? Then finally we discussed about the role of phenolic acid, phenolic compound as antioxidant. How do it do? So what is the role? Role is very important. So we can explain using resonance structures and electron deglobalization system. Right? Resonance structures and electron deglobalization. We can do phenolic compound can do the role as antioxidant. Right? So that is the third category is very important. Very important means instead of natural antioxidant, nowadays there are artificial antioxidant in the market. Based on our Food and Drug Act, we can use standard doses. Based on our Food and Drug Act in Sri Lanka, right? We can use standard sources. So artificial antioxidant, few examples: butylated, hydroxy, toluene. Butylated hydroxytoluene, short form is BHT. Butylated hydroxytoluene. Butylated hydroxytoluene. Butylated hydroxytoluene means BHT. Right? The second example is again butylated. Other part is same hydroxy. It is not toluene, anisole. That is BHA. BHA, butylated toluene and butylated anisole. Butylated anisole, that is BHA. Right? Then gallic acid. Gallic acid. GA. Gallic acid. That is GA. All these are artificial antioxidants which contain highly reactive phenolic group in their system. Right? If you go through the internet to any organic chemistry source, you can observe the structure of all these things. Then, when you observe all these things, you can observe the highly reactive phenolic group available in the system. Phenolic group available in the system. Right? That's why they act as artificial antioxidants. Activity is same as the other natural one. Right? Right. Then we think about what is the impact of oxidation. Impact of oxidation. What is the impact? What do you think? Why do you worry about this oxidation? Why do you worry about this oxidation? Right? First important point, when free radical form due to oxidation, this free radical first interact with the muscle proteins. And due to this interaction, protein get denatured. Right? Protein get denatured. That is biochemically, that is very dangerous. Our next topic, we will going to study proteins. Right? Then under protein, we will see what is denature and what is the impact of denature on biochemical reaction. Right? That is very dangerous thing. So this thing can be happen due to the free radical formation. That is first problem associated with fat oxidation. Right? The other one, because of denaturation of the protein, would become very hard. Muscles become very hard. Right? If the free radical is there, muscles become very hard. Now, don't mislead others. If your muscles get hard, free radical content of your body is very high. That is not the information. Right? Information is, if the free radical content is very high, protein get denatured and the food get hard. Texture is little bit hard. Right? Then, not only that, if it hard, water holding capacity of that system is decreased. Water holding capacity WHO. That is not World Health Organization. WHO means water holding capacity. Sorry. Water holding capacity. WHC, water holding capacity is very low. Right? So, what will happen? First, interact the free radical with the protein. Protein get denatured. Then, texture become hard. Water holding capacity of the system is very low. Right? Then, gradually, food become unedible. So, you cannot convert it into edible condition because of the free radical. Right? Then the second important point is, among the products, terminal products, there are aldehydes. Among the final products of the fat oxidation, there are aldehydes. So aldehydes are responsible for the other reactions. Glycation reaction is one important. Diabetes-like conditions, right? Rapidly increase with the free radical level, right? Because if there is aldehyde, glycation reaction set of reaction can be happening, right? Without sugar, right? So there is a risk. Other one, if the food process is like this, if you think about a food without a human body, if you think about a food, if the formation of aldehyde is there, aldehyde can interact with the protein again and undergo special reaction. When we learn about the Brownian reaction in food, use it with food chemistry, you can learn that reaction in detail. But for this level, you should know when aldehyde interact with the proteins, right? There is a complex set of reaction. This is Maillard reaction. Complex set of reaction is Maillard reaction. Maillard reaction. This is actually Brownian reaction. Due to this reaction, color of the food can be changed into brown color. Color of the food can be changed into brown color. In detail, you can learn this reaction at the next level. Next level means second year. In your second year food chemistry lectures, right? Start with this kind of Brownian reaction. This is one type of Brownian, right? This is the other impact, right? Right. The third one. Third impact is the actually fat get oxidized and decrease the amount of fat. The direct impact is right for the fat soluble vitamin. What happens to fat soluble vitamin? The medium decrease. Fat soluble vitamins, fat is the medium. When it oxidizes, medium decrease. Therefore, availability of fat soluble vitamin decrease. Availability of fat soluble vitamin in that food is decreased. Right? These are the major problems associated with fat oxidation. Major problems associated with fat oxidation. If I take one by one very rapidly, first thing, right, formation of free radical is there. That free radical interact with the protein and protein denature. Due to denature, protein become very hard. System become very hard, and water holding capacity decrease. Not only that, among the products there are aldehyde-like compound. So those aldehyde compound interact with the protein and form brown color. That is Brownian reaction. Not only that, fat soluble vitamin level also decrease because fat content decreased due to oxidation. Right. So these are the direct impacts of the fat oxidation. That's why we try to protect this oxidation. That's why we try to protect this oxidation. Right?